Hey guys, welcome back. Okay, so far all the solving trig equation problems that we've done have always had just a plain old x or theta as the argument on the trig function. So the next step in the solving trig equation world is to make that argument fancier, something kind of like this: 2 times cosine 3x minus 1 equals 0. So it's not a plain old x or theta anymore. It's got something there with it. First off, be aware that if I had written this exact same problem as 2 cosine 3x minus 1 equals 0, you would know that the minus 1 is not part of the argument, because if it was part of the argument, it would have parentheses around the whole thing. All right? The argument is always the terms that are directly stuck to the trig function, but anything that's added or subtracted is separate from that argument. So if you just had 2 cosine 3x minus 1 equals 0, you can be confident saying that the 3x is the argument and the minus 1 is just an extra number on the outside. So I'm going to add 1, divide by 2. I have cosine 3x equals 1/2. Cosine is adjacent over hypotenuse, so I'm going to look for a positive 1 adjacent, a 2 hypotenuse. That makes a 1, 2 square root of 3, and a 1, 2 negative square root of 3. We have little 60-degree reference angles. So the angles that are the answers that we're looking for is 60 and 300. Now writing these in radians, we would have pi over 3 and 5 pi over 3. And based on the way the angles are set up, we're going to spin in full circles for each of these angles. So normally the answers we would have at this point are x equals pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. But this time it's not a plain old x. It's a 3x. So when we solved for these angles, we found not x equals, but we found 3x equals pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. So for this type of problem, the problem with the fancy arguments, you solve them all the way just like normal. You add in the plus pi n or the 2 pi n, whatever it's going to be, and it's only at the very end that we're going to deal with whatever's here with the argument. To get rid of that 3, we're going to divide everything on both sides by 3. And that's going to give us x equals pi over 9 plus 2 pi over 3n and 5 pi over 9 plus 2 pi over 3n. And there it is. You treat these problems the exact same all the way until the very, very end, and only at the very, very end do you then deal with the fact that it's a fancy argument. Let's try something else. Take a look at 3 tangent x over 2 plus 3 equals 0. Go ahead and pause the video, try this problem, and come on back when you have it. So I'm going to go minus 3, divide by 3. So I have tangent x over 2 equals negative 1. That can be negative 1 over positive 1 or positive 1 over negative 1. Either way, it's SOHCAHTOA. And so I'm looking for an opposite of negative 1 and adjacent of positive 1. I've got a 1, 1 square root of 2. An opposite of positive 1 and adjacent of negative 1. Again, I have a 1, 1 square root of 2. So my little reference angles are 45s. And the angles that I would be giving as final answers would be the 3 pi over 4. And then because these two angles make a straight line, we're going to spin in half circles pi n. That'll go from one angle to the other infinitely, giving us both of those answers. And again, normally it would just be x equals 3 pi over 4 plus pi n, but we have a fancy argument, so it's going to be x over 2 equals 3 pi over 4 plus pi n. So now to deal with the fact that it's a fancy argument, now that we've got the whole problem almost done, we're just going to multiply by everything on both sides by 2. So I have x equals 3 pi over 2 plus 2 pi n. And that's it. Now, if these problems were on an interval, say on 0 to 2 pi or something sort of like that, just some sort of interval. That selection of the final answers doesn't happen until the very, very end. We would have the spinny part in there, and only then would we start plugging in different values for n to see what fits on the interval. Try this problem, see what you can come up with. 10 sine theta plus 30 equals 5 rad 2. Pause the video and give it a shot. I'm going to divide by 10, divide by 10. So I have sine theta plus 30 degrees equals rad 2 over 2. I can unrationalize, so I have sine theta plus 30 degrees equals 1 over rad 2. Sine is opposite over hypotenuse. So the triangles that I'm dealing with are 1 square root of 2 and 1 negative 1 square root of 2. The opposite over the hypotenuse is both 1 over rad 2 in this case. So I have a little reference angle of 45, a little reference angle of 45. So I have 45, and we're going to spin in full circles, so plus 360n. And I'm going to have 135 plus, spinning in full circles, 360n. And again, this would normally equal just plain old theta, but it's a fancy argument this time. So we have theta plus 30 equals 45 plus 360n and 135 plus 360n. So now to get theta all by itself, I'm going to go minus 30, minus 30, minus 30. I get theta equals 15 plus 360n and 105 plus 360n. I'm being a bit lazy with my degrees here, but that would be our final answer. All right, now these problems get just as interesting as they did before, but now they can have a fancy argument going with them. Before we move on to something like that, though, let's back up to a problem like this first problem that we did. I mentioned an interval. I said, say it was on 0 to 2 pi. It's only at the very, very end that we're going to actually figure out the values that are on the interval. So in this case, if we have 2 pi n as the end point of the interval, we look at the denominators that we're dealing with. We have pi over 9. It's going to be easier if we're working with the same denominators. So 2 pi, I would give a denominator of 9, making it 18 pi over 9. That at least puts us on the same, we're speaking the same language in terms of the fractions. So we simply start letting n equal different values, and we see if it falls between 0 and 18 pi over 9. So if n equaled 0, we would have pi over 9 plus 0, so we would have x equals pi over 9, and that falls between 0 and 18 pi over 9. If n equaled 1, we would have 2 pi over 3, which multiplying by 3 over 3 would give us 6 pi over 9. 1 pi over 9 plus 6 pi over 9 makes 7 pi over 9, which does fall on the interval. And now you can see how the terms are growing by 6 pi over 9 every time we create a new value for n, every time we set n to the next value. So the next value is going to be 6 pi over 9 later. It'll be 13 pi over 9, and that also falls on the interval. And the next one would be 19 pi over 9, which is off the interval, so we're not going to count it. So then we jump to the next term, the next answer. We set n equal to 0. We get 5 pi over 9. We're again moving in chunks of 6 pi over 9. I just multiplied by 3 over 3, and I found that it's 6 pi over 9. So if n equals 1, we would have 5 pi over 9 plus 6 pi over 9. That's going to be 11 pi over 9. Moving another 6 pi over 9 would be 17 pi over 9, and going another 6 pi over 9 would take us off the interval. So we would have 1, 2, 3, 4, 5, 6 different answers if we were working with the interval 0 to 2 pi. So it's important because of the way the interval changes. Instead of a 2 pi n interval, we had a 2 pi over 3n interval. So it's important to wait till the very, very end to find the solutions that are on the interval that they might be given in the problem. Otherwise, you would skip out. Otherwise, you would miss several of the possible answer choices. Okay, so now let's try one of those problems that I was talking about that is much more interesting. Take a look at 3 times cosecant squared x over 5 times cotangent 4x equals 4 cotangent 4x. Pause the video and try it on your own, see what you come up with. Now I know I'm not allowed to completely divide information away because then I lose that information, but I am allowed to divide by a variable term if I also set that variable term equal to 0. So what I'm left with is 3 cosecant squared x over 5 equals 4, and cotangent 4x equals 0. So on the left-hand side here, I'm going to divide by 3, divide by 3. I get cosecant squared x over 5 equals 4/3, square root, don't forget your plus or minus. I get cosecant x over 5 equals plus or minus 2 over rad 3. And when we have a plus or minus, I like to separate them. It's going to be cosecant x over 5 equals positive 2 over rad 3, and cosecant x over 5 equals negative 2 over rad 3. So I'm looking for a hypotenuse of 2 and an opposite of positive rad 3. That makes a 1, 2 squared of 3. Again, a hypotenuse of 2, an opposite of positive rad 3. And then I have a hypotenuse of 2 with an opposite of negative rad 3. And a hypotenuse of 2 with an opposite of negative rad 3. Those make little 60-degree reference angles. And while the spacing looks promising, you'll see that between these two angles is 120, between these two angles is just 60. 120 and 60. So we don't have even spacing all the way around. What we do have, however, is one angle plus a back-to-back partner, and then another angle plus a back-to-back partner. Before I write the final answer for that branch of the problem, I want to come back to the cotangent 4x equals 0. I'm going to turn this into sine and cosine. Cosine 4x over sine 4x equals 0. Multiplying both sides by sine 4x. That gives me cosine 4x equals 0. When does cosine equal 0? That happens at 90 and 270. And looking at it on a graph, that happens at 90 and 270. Adding that into this problem doesn't create even spacing all the way around. So I'm going to keep my answer as pi over 2 plus a straight line n times. But instead of equaling plain old x, it's going to equal 4x. So for the right side branch, we have divide by 4, divide by 4. We get x equals pi over 8 plus pi over 4n. And then for the left side of the problem, we have 60 degrees is pi over 3 plus the straight line makes pi n. 120 degrees is 2 pi over 3s plus a straight line is pi n. And this time our fancy argument is x over 5. Multiplying everything on both sides by 5, we get x equals 5 pi over 3 plus 5 pi n and 10 pi over 3 plus 5 pi n. So these two answers combined, so we have 1, 2, 3 answers total, solve this problem for us. All right, let me know if you have any questions and have a wonderful day.